say that, I'm sure this is true of some of you. I think a lot of us have been fascinated by chirality for a really long time, like whole scientific lives. By the way, how many people have taken intro organic? One. Okay. Two. Okay, so that's pretty nominal. I'm often entertained by what some physicists sometimes say about chirality. Anyway, I'm going to start with molecular chirality because chirality in liquid crystals kind of, starts with molecular chirality, but not necessarily. But there's actually a lot of lessons to learn about chirality in general and chirality in liquid crystals by thinking about molecular chirality. Because molecules are much more dynamic, and actually it's exactly the same phenomenon as liquid crystals. Molecules are, which I'll try to convince you. It sounds like a non sequitur, but I think it's true. Okay, so the physicists came up with the most beautiful experiment in the history of physics, and so the chemists felt jealous, and they had to come up with the most beautiful experiment in the history of chemistry, and this was by a vote of some number of people. I don't happen a while back, but this Louie Pasteur experiment, where he first proved that molecules are chiral. This was judged to be the most beautiful experiment in the history of chemistry. I'm happy to show it here because, Pasteur was French, but he was given the Rumford Medal by the Royal Society in 1856, and Lord Rothley wrote this fantastic sort of statement about the why Pasteur had won the Rumford Medal, and it's just gorgeous. The writing is incredible. I really like it, but the bottom line is that Pasteur had seen that you could crystallize this mysterious material. It was called racemic acid. So this actually was work that was stimulated by the French wine industry, and they make wine in France in these giant vats, and they had a batch of wine go bad, which was an economic disaster. But they isolated several kilograms of this new compound called racemic acid, meaning it came from grapes, and Pasteur, all the scientists were trying to understand what racemic acid was, and in fact the chemistry community worked on that one sample of stuff for probably 40 years. Pasteur was the one that finally figured out what was going on, but this stuff was very similar to tartaric acid, which was known to occur in wine. And there's a famous chemist in the day, Mr. Lick, who, they used to look at crystal morphology to determine whether two compounds were the same or different. And so they had all the racemic acid was an acid, so you can make salts out of it. So Mr. Lick had made this sodium ammonium salt, racemic acid, and he declared that those crystals were isomorphous to the tartaric acid sodium ammonium salt crystals. Therefore, racemic acid had to be tartaric acid. But there was a little problem, and that is that tartaric acid it was optically active, it had rotatory powers. And the salt of tartaric acid would rotate the plane of polarization, plane polarized light passing through the sample, whereas racemic acid was optically inactive. And yet, they thought that, some people, a lot of people, thought it was exactly the same stuff. They just ignored the rotatory power because they didn't understand it, Okay, so it's the same. And Pasteur thought that sounded weird. He was a postdoc, and at age 26, he was looking, and he thought, that's weird, that can't be right. He was a crystallographer, and they used to use rotatory power in optics a lot. So he crystallized the sodium ammonium racemate in France, and the later was quite cold, and he got these conditions where it turns out that racemic acid is racemic tartaric acid, right? I mean, that's where the term racemic comes from. It means a 50-50 mixture of right-handed and left-handed molecules. So somehow in this wine vat, the tartaric acid had racemized. Okay, and so it started out one pure enantiomer and ended up a 50-50 mixture of enantiomers. And so this is racemic acid is a 50-50 mixture of these two. One of these is naturally occurring tartaric acid, and the other one came from somehow this racemization that happened. And it crystallized out, and that's where they got this big giant kilos of stuff in this wine vat. So Pasteur crystallized this stuff, and he looked in the microscope, and he noticed that, the crystals are homeomorphic, or isomorphous to tartaric acid crystals, but he noticed that there were these hemihedral faces on the crystal, which makes the crystal macroscopically chiral. So you can look at the crystals in a microscope and tell the difference between right-handed crystals and left-handed crystals. You can do the same thing with quartz. Okay, you can see the right-handed quartz crystals and left-handed quartz crystals. Okay, so Pasteur separated these crystals with a dissecting needle under the microscope. He ended up with two little piles of crystals, one right-handed and one left-handed. He dissolved them in water. One of them rotated plane polarized light clockwise. The other rotated the same amount counterclockwise. And this was in solution. So that means the molecules had to be chiral. It wasn't just the crystals. Okay? So this was the foundation of the structural theory of organic molecules and the structure of organic molecules, and really was, was an incredibly beautiful piece of work, I would say. And so the geologists had already coined the term conglomerates. And so I asked Noel. Noel's a physicist, of course. This is a physicist I've been working with for many years. He'll be here later in the week. But I asked him what he thought conglomerate meant, and he said, well, it's a giant international company. Of course, that's what a conglomerate is. But in geology, a conglomerate is a rock that contains right-handed and left-handed crystals. So a mixture of macroscopically chiral, right-handed and left-handed crystals, these macroscopic domains, that's kind of important. It's not molecular. Macroscopic domains of right-handed and left-handed crystals in a rock, that was called a conglomerate. So Pasteur called this mixture of right-handed and left-handed tartaric acid crystals, right, where the right-handed molecules are all in the right-handed crystals and the left-handed molecules are all in the left-handed crystals. So you've actually separated the right-handed molecules from the left-handed molecules spontaneously in this crystallization. Okay? And he called that an organic conglomerate. Okay? It's a kind of conglomerate. And exactly. And so this was actually the first resolution in history. That was the first time anyone had ever separated chiral molecules of, a mixture of right-handed and left-handed molecules and ended up separating them. He did this by separating the right-handed and left-handed crystals in a microscope, and then his students went on to invent basically almost all the ways we use now of resolving racemic materials, except chromatography. But and this kind of crystallization of conglomerate, crystallization to separate enantiomers is the most important way of making enantiomerically pure drugs. And so this is an important technology that's still used today. Okay, so we have these chiral molecules, and well, as I say here, Pasteur knew that he had proven the molecules were chiral. And if you look at what he said, okay, so this is third hand, but it's all like, you can track through this list of publications, and Pasteur basically realized that the molecules had to be chiral, but there was no molecular structural theory in 1848, so he had no idea, really what the structure of the molecules were. But look what he speculated. He said, well, this is right-handed acid grouped in spirals of a right-handed helix, or maybe they're placed at the summits of an irregular tetrahedron. So he already had the tetrahedral carbon, but he didn't really know it. And he called these things dissymmetric. So dissymmetric is a synonym for chiral. Because chiral things don't have to be asymmetric. They can have symmetry. They can have rotation symmetry. Okay? But they just can't have any reflection symmetry. So Pasteur made up this word dissymmetric, and then Kelvin came along many years later and made up the word chiral, and everybody thinks of Kelvin, but nobody realizes that Pasteur really, had a term that actually tells you more about what's going on. And, so Pasteur understood that the molecules were chiral, but, the chemists in those days, in the second half of the 18th century, weren't really, 19th century, weren't really ready to understand this, because they really thought that, the molecules had unrestricted movement. That is, if you had, they understood that there was valence and chemical bonds. So, atoms could stick together in these covalent bonds, these chemical bonds. But they didn't think the molecules had any Euclidean geometry at all, that the groups connected were just completely free to move around any way they wanted. And without that kind of Euclidean geometry, you really can't have chirality. Okay? So they understood that atoms are connected in compound molecules. Kepler certainly did. and so did Cayley, which we'll get to, because Cayley was at Cambridge, and so I have to tell the Cayley's story. But anyway, so yeah, so Kekule, one of the most famous chemists of his day, this was important to him, this unrestricted movement, because it allowed him to interpret experimental results. The results were right, the interpretation was wrong, but anyway, that's what he was doing. So without some kind of constraints on geometry, right? You can't get chirality. And what do I mean by chirality? Okay, in chemistry, a chiral compound has to be resolvable. I mean, almost every liquid crystal there is, has chiral conformation. Sometimes it's chiral. But those conformations are in rapid dynamic equilibrium. There is a lot of unrestricted function. And so chirality in chemistry, when I say a chiral compound, I mean that you can actually separate that compound into right-handed and left-handed molecules that maintain their identity even after you dissolve them in a solution or heat them up or whatever. They're still right-handed or left-handed. We call that resolvability. Pasteur did the first resolution. If something is resolvable, it has to be chiral. So there's a difference between a chiral structure and a chiral compound. It has to do with allowed molecular motions. All right, these were the kinds of structures that Kekule was using in 1861 to describe molecules. They had no Euclidean geometrical constraints. Okay, so Cayley actually made a big splash. This guy is incredible. I love him. He graduated the senior wrangler in 1842 from Trinity College. It means he got the highest score on the math test, I guess, at the end. And then he became a lawyer, and he was making money, but he loved math, and so he quit his lawyer job and became chair of math at Cambridge, where he made no money, but he published 966 papers. He was happy. And he invented a lot of mathematics. Okay? And one of the things he invented was, graph theory. Graph theory is this abstract graph theory is a kind of topology, it's a branch of geometry, where only, where no metrics are invariant. Okay? So objects are infinitely flexible, but you can't, break a line or pass one line through another. Okay? So, he developed this topological abstract graph theory to actually, for a practical reason, which was to predict the number of isomers, we now call them constitutional isomers, possible for a saturated hydrocarbon with the molecular formula CnH2n+2. So that's just, all saturated carbons. So if you have, one carbon, then there's only one isomer, methane. If you have two carbons, there's only one isomer. If you have three carbons, then there's one isomer. But if you have four carbons, then there's two isomers, N-butane and isobutane. This has to do with the way the atoms are connected. Now, you got to realize that a lot of people at this time didn't really believe that you could understand how the atoms were connected or that they were connected. It was just kind of the famous, fruit pudding or whatever they call it model for a chemical structure, right? But, Cayley said, gee, I'm going to invent this thing called a quartic tree, which is just a graph where every vertex is. So a graph is just a set of vertices and edges connecting some of the vertices, not necessarily all. Okay? That's a graph in topology. And so Cayley said, well, let's just make these vertices be the carbon atoms, and we'll just fill the valence to 4 with hydrogens. So we can ignore the hydrogens; they're just always there. Each vertex has a valence of 4. And then we can predict how many, he proposed that the number of isomers was going to be the number of non-homeomorphic graphs. Okay? Non-homeomorphic meaning, they're distinct topologically. You can't deform one into the other without breaking the line or reconnecting those. Okay? And you're probably familiar with topology. Okay, so anyway, he predicted the 2 isomers of butane, which were known. But then he went to 5 carbons, and he predicted some number of isomers, 5, I guess, and nobody had discovered. Some of these isomers weren't known. So there was a smaller number of known pentane isomers than what he predicted based on this graph theory model. So the chemists went in and looked around, and sure enough, they found those isomers. And that was a major piece of evidence suggesting that the atoms in these molecules had to be connected in a certain way, in an order, right? But still, he had no Euclidean geometry. Like in graph theory, there's no Euclidean metrics, right? No metrics are invariant. Lines can be any length, they don't have to be straight. It's just the connectivity You know, there's a key concept in chemistry, and Cayley really came up with this. Okay, but Cayley and Kekule, this Cooper, Loschmidt, Berthelot, these are famous organic chemists from that era. None of them was able to explain Pasteur's isomers. You know, they didn't understand what these isomers that Pasteur had isolated were doing, right? These right-hand, the right-hand and left-hand tartaric acids. So that was still kind of a mystery. And the reason was because, they thought the molecules had no Euclidean geometry. Okay, so now the guy that finally explained Pasteur's isomers and kind of moved us into the realm of chemical chirality was this Van Hoff, who won the first Nobel Prize in 1901, but it wasn't for, Van Hoff suggested the tetrahedral carbon. That's the thing he's famous for, right? He was a young guy. He was, 22 years old, and, he's messing around with structure of organic molecules and came up with this idea that he could explain a lot based on the idea that tetravalent carbon was tetrahedral, and not only it was tetrahedral, and those angles were fixed. I mean, there were constraints on the kind of internal motions that the atoms could undergo inside one of these compound molecules. Like there were bond angles that were invariant, right? So in the tetrahedral molecule, you got these 190-degree angles, and you can bend them a little bit, but not too much. So there was this Euclidean geometry in molecules as well as topology, and this explained a lot. It explained why there's only one isomer of CH2Cl2, for example. Okay. Kekule had another way of explaining that, which was complete motion. But as opposed to anybody else, and by the way, he was roundly ridiculed for this. The most famous scientists of the day were just saying, they were publishing papers saying, this guy is really crazy. This is the most ridiculous thing. You can't, it's just impossible. Anyway, he turned out to be right. And then many years later, he won the first Nobel Prize, that was 1901, for inventing physical chemistry. So he was Dutch, and in the Netherlands at that time, they decided that they would teach all the students, the young students, mathematics, which was not done in Germany or anywhere else. So they had this math training, and Van Hoff decided that he would try to combine chemistry with math, and he invented physical chemistry and won the Nobel Prize in 1901. And he also chaired this famous Bunsen colloquium on the nature of liquid crystals, which, according to the story, almost led to a fist fight between these two arguing scientists. And Van Hoff had to go in there and physically separate them. That's the story, anyway. It's published. I don't know if it's really true. But so he finally explained Pasteur's isomers. Once you have the tetrahedral carbon, you could easily see the molecules to be chiral, and so you could get right-handed and left-handed molecules. Okay, so that was Van Hoff. He's a real hero because he invented the tetrahedral carbon and invented physical chemistry and stopped these guys from fighting in the Bunsen colloquium, but also because he looks just like Sven Lagerwald, who's one of the famous liquid crystal physicists. Okay, so here's Kekule and here's Van Hoff back here. These guys were contemporaries, and so they were at a meeting and somebody took a picture. So Kekule was older than Van Hoff. All right. So okay. So then you can ask the question, why didn't Kekule propose the tetrahedral carbon? Kekule had this, he had his supreme principle was that, the molecules had unrestricted movement. And the reason for that, the reason he thought that was because if you look at dichloromethane, there should be two isomers of dichloromethane. And yet there was only one. So he said, well, that must mean that these atoms can move around that are connected to the carbon. He didn't come out into the third dimension and invent the tetrahedral carbon. Instead, he just said that there's unrestricted movement. And his theory worked really, really well. I mean, this idea of connectivity of atoms worked very well to describe, the ortho, meta, and para isomers on a benzene group, of the dichlorobenzenes. And he even invented this concept that, this ring with double bonds here and here had to be somehow in dynamic equilibrium with this ring where there was a double bond between the two chlorines. Otherwise, you would have two orthodichlorobenzenes and there was only one. So this counting isomerism you know, isomerism, both stereoisomerism and constitutional isomerism. So if molecules differ in their connectivity, like this one and this one and this one, they differ in their connectivity. The molecular graphs are non-homeomorphic. Okay? So those are called constitutional isomers. And stereoisomers happen because of Euclidean geometry and tetrahedral carbons. Okay? So stereoisomerism is Euclidean, constitutional isomerism is just graph theory, is connectivity. And you know, so okay, so there is an unrestricted movement. There's only one dichloromethane because the carbon is tetrahedral. And so there's only one isomer of dichloromethane. Okay? But there's also only one isomer of dichloroethane. Okay? Yet dichloroethane exists in these two kinds of conformations. So we know now that you can rotate around the single bond, and so that's why there's only one dichloroethane. There is some unrestricted movement. It's just that it's a the beauty of organic structure in this context is it's a combination of topology and Euclidean geometry. But those two things are completely separate, so here's the basic way that people think about isomers. You know, a chiral object is not congruent with its mirror image, the non-superposability of mirror images, like Pasteur said. You know, non-superposable mirror images, those objects are chiral, okay? So, non-congruent, okay? And chiral objects lack reflection symmetry. So, you know, you can always, if you want to decide if something is chiral, it doesn't matter what it is. If you want to decide whether something's chiral or not, then you take the object, you take the mirror image, you make these two models, or you have two objects that are mirror image, you try to superpose them. If you can't do it, they have to be chiral. Okay? If you can't do it, then it has to be achiral, or not chiral. Okay? So, but wouldn't it be great if you could just look at one object and decide whether it's chiral or not, without having to make the mirror image and see if they're superposable? So, you know, that's where this concept of point group symmetry comes in. It's extremely handy in both organic molecules, and we also use it in a very ad hoc kind of imprecise way in crystals. But, you know, so basically you look at the object and you look for symmetry operations that you can perform on the object. So the symmetry operation is there's only two kinds, real simple. You can either do a rotation, a rigid rotation, or you can do a rotation and then reflection normal to the axis that you're rotating around. So you can have a rotation, reflection, or rotation. That's it. Those are the only two kinds of, those are the only two symmetry operations. So you look at your object and you find out, you sort of list all the possible symmetry operations. Right? You can have well, everything has a 360-degree rotation. You have to do the operation and end up with something that's indistinguishable from what you started with. Obviously, any rotation is going to give something that's the same as what you started with. But in chemistry, there's lots of levels of sameness. Okay, so if you do a rotation and end up with something that not only is the same, but is indistinguishable, it's the same. In other words, they can be sort of brought to superimpose by purely translation with no rotation. Okay, so if you do a rotation and you see something that's indistinguishable from what you started with, then that's an element, that's a symmetry element of the object. You just make a list of all the symmetry elements that the object has, and you make a group out of that, and that's the point group. And they have these funny names, but it's really very simple. Okay, this shows these point groups, and for objects like molecules, this is very rigorous, and you can look at the symmetry for rigid molecules anyway, and decide what the point group symmetry is. And so if you have only rotation symmetry, then you have to be chiral. If you have only rotation symmetry, that includes, by the way, a 360-degree rotation. Now, some people will say, well, that's no symmetry. But there is this rotation axis, right? 360 degrees. It always comes back to where you started. Okay? So, if you have only rotation symmetry, that's twofold rotation, 3, 4, 5, n-fold rotation axes. And you can have, orthogonal ones. You can have more. You can have 3 kinds of rotation axes, and the object has to be chiral. If you have any rotation reflection, so that includes a 360-degree rotation and reflection, which is also known as a mirror plane. I mean, almost everybody would say, well, that's just a mirror plane. But it's really a rotation reflection where the rotation is 360 degrees. Okay, in one way. Okay, so if you have any reflection symmetry, in any of the elements of the group, then the object must be achiral. That's that. Okay. And by the way, in chemistry, an object with, so this show and fleece symmetry, so if you have only rotation, then a chemist would say that molecule has chiral symmetry and is chiral and not superposable on a smear image. Unfortunately, in physics, chiral symmetry kind of means something different. It effectively means achiral. So in physics, the term chiral symmetry breaking actually makes sense. But in chemistry, it's a total non sequitur. Because how can you break chiral symmetry and end up with something chiral, right? You're breaking achiral symmetry to get chiral. Okay? So if you talk about chiral objects having chiral symmetry, then that's not going to work. So this kind of has led to a lot of, but of course chemists use chiral symmetry because it sounds really cool. And they never really think about what it might mean. But anyway, if you have only reflection symmetry, you have chiral symmetry, and objects can be chiral and have, non-trivial symmetry, right? I mean, here's tartaric acid, one enantiomer. This molecule is chiral, but you can see it has a twofold rotation axis normal to the screen, right? So if I have a line passing perpendicular to the screen right through that point in the middle, if I rotate 180 degrees around that axis, then I end up exactly at the same place. So that molecule has symmetry, but it just has no reflection symmetry, so it's chiral. That's why Pasteur said dissymmetric instead of asymmetric. Okay. All right, so so this is the conventional stereochemistry. This thing that all the three people that took organic have seen before. Okay, so we separate topology from Euclidean geometry. So one kind of isomer, this is about isomers. Okay, so one kind of isomer is purely topological, it's just about connectivity. They're called constitutional isomers. Constitutional isomers have different connectivity, right? The graphs are non-homeomorphic, all right? So, if you start with some structure, if they have, these are actually pairwise descriptors. These terms that chemists are always throwing out, like enantiomers and diastereomers, they're pairwise descriptors. You have to have a pair of things. You describe their relationship with one of these words. Okay? So the two things can have different molecular formula, and if they have different molecular formula, meaning different numbering kinds of atoms, they have to be different. That's pretty obvious. But they can have the same molecular formula, and they can have the same connectivity or different connectivity. If the connectivity is different, the molecular graphs, Cayley's term, these graphs, right, that's the structural formulas we use today are molecular graphs. And some of us call them molecular graphs, because that's exactly what they are. They have coloring, right? The atoms have different colors. Your color is a color graph. Okay? So if the connectivity is different, then we call those constitutional isomers. That's purely topological. If the connectivity is the same, then the graphs are homeomorphic. And over here, everything is purely Euclidean, right? The things are congruent. Two structures that are congruent. You have to have a pairwise descriptor for two molecules that are the same. Homomers. Okay, they're always mers, something mers. Okay, so homomers, and then if they're not congruent, they're stereoisomers. Okay, and then the stereoisomers, either they can be mirror images, in which case they're enantiomers, or they're not mirror images, and they're diastereomers. And this, of course, is the one that drives the sophomores crazy into organic. But it is possible to have, these things that have, homeomorphic molecular graphs. They're not congruent, and they're not mirror images. So those are diastereomers. Okay. So stereoisomerism, which is where chirality comes in, it's about lack of unrestricted movement. It's about some kind of constraints on these internal motions of the atoms. That's where chirality comes from. Okay? Except, that's not really quite told. Well, okay, so here's Kepler and Cayley are talking about constitutional isomers. They were ignoring this molecular rigidity, these constraints on the motions. And then over here, you've got Pasteur, Van Hoff, and Lebel, who finally realized that there was this Euclidean geometrical aspect to it. It wasn't just topology. Okay. So enantiomers are isometric but non-congruent molecular graphs. They're chiral. Isometric means all the exact same lengths and angles. All the metrics are the same, but they're not congruent. They have to be mirror images. All right, so it turns out that all that stuff that I just said works fine for rigid objects. But molecules are usually not rigid. And chirality, molecular chirality, is actually really, really interesting and much deeper and more subtle than most people think, most chemists do. Okay, so you know, a chiral molecule doesn't mean a molecule that lacks reflection symmetry. It doesn't mean a single structure that lacks reflection symmetry. What it means is that there's no way that, you know, the molecule can get to its mirror image by allowed motions, you know, internal motions of the atoms. That's what in order to be resolvable, and you dissolve the stuff in solution, if the molecule has lots of allowed motions, you can, you know, if those motions will allow it to get to its mirror image, the thing's achiral. You know, so you have all these different motions that are, you have to look at the symmetries of all the possible configurations of the atoms of the molecule, given this flexibility, the lack of you know, given this motions that are allowed. And then you can resolve the stuff. So when a chemist says a compound is chiral, what they really mean is that you can resolve it into enantiomers that have their own identity and they're stable for some, you know, period of time, which means that the definition of isomers has to do with the conditions of the experiment, right? There's a lot more isomers close to 0K than there are at room temperature. Almost, you know, almost everything's chiral close to 0K. But if you let them warm up and they get all these dynamics going, then they're achiral. And a lot of people hate this and they feel very uncomfortable about it, but I think it's the only way. You have to deal with you have to say at room temperature, and then you have to say the time scale. They're not interconverting at room temperature on some time scale, like say a couple of days. Because that's arbitrary enough, right? I mean, you got to pick something. Okay? It's chiral if it's resolvable and then stable for a couple of days. Okay? And there's lots of things that, you know, they would racemize over time. I mean, everything racemizes. Amino acids racemize over time. It's like geological time scale. So they can, you know, they can look at the, you know, at the enantial purity of these amino acids in, you know, biological specimens from the beginnings of life, and they can tell how long those things have been around. Okay, so yeah, a chiral compound is an ensemble of chiral molecules that, you know, can interconvert with the mirror image, and an achiral molecule, of course, cannot be resolved into enantiomers. Even okay, so here's the cool thing. An achiral molecule cannot be resolved into enantiomers. That means the achiral molecule, one conformation, it can deform into the mirror image so that you can't resolve them. Okay? Guess what? Some molecules, some achiral molecules, can never be achiral, rigidly achiral. So you have this achiral molecule, but it's always chiral, which just shows you how lame the language of stereochemistry is. But you know that we're stuck with it. Not much we can do. But yeah, the bottom line is that chirality is about lack of unrestricted movement, except when it's not. So is molecular chirality only about constraints on internal motion? Well, no, not really. But you know, but the exception proves the rule that usually it has to do with rigidity, constraints on motions. Okay, so you know the exception is these topological stereoisomers. Okay, so you know here you have a ring of carbon atoms, say 50 carbon atoms in a ring, and you tie those atoms into a knot. Okay, so here's a left-handed trefoil knot, and right-handed trefoil knot. Okay, obviously you have to break a line to turn this into this. You have to break a bond and then reconnect. So that is not going to happen. There's no way you can go from here to here under any conditions where the bonds are stable at room temperature for days. So, and then these two, you know, right and left-handed knots. By the way, almost all knots are chiral. So the mathematicians have no name for chiral. They only have a name for achiral. They call them amphichiral, right? There are rare knots that are achiral, so they're amphichiral. But but they don't really have a name for chiral because to them everything's chiral. It's the achiral ones that are unique. So you don't have to have a name for the chiral ones. Anyway, so the trefoil is chiral, and so the left-handed and right-handed trefoil knots are, they're enantiomers, and there's no way for them to interconvert, and so these are kind of, here's where the topology and the connectivity kind of merge, right? These are not constitutional isomers, they have homeomorphic graphs. These graphs are homeomorphic, all three of them. They have exactly the same connectivity, right? I could tie a knot in this, and then connect. And this thing, if I follow around, we're ignoring, this has to do with embedding in space. This is not intrinsic topology. Intrinsically, these two things are the same. If you could go into higher dimensions, if you're not embedded in space, all three of these things are the same. They're homeomorphic. They have exactly the same connectivity. You know, you follow the line around, and the connectivity is exactly the same. But when you stick them in three-dimensional space, suddenly you get these extrinsic properties that jump out, like you can't interconvert the two trefoils when you're embedded in space without breaking the line. Okay? So these things are, so here's a case where the connectivity, gives you the chirality. Okay, it's not, it's like the constitution itself makes the molecule chiral. There's no Euclidean rigidity required, right? These things can take up an infinite number of possible shapes. All three of these, right? You can do whatever you want to them, stretch them. I mean, in topology, there's no lengths, no angles, just connectivity. Okay. So, and yet there's no way to get this to this, and so those two things are chiral by this definition that we propose. So, here you've got the constitution, sort of giving you these topological stereoisomers, whereas normally stereoisomers have to do with Euclidean rigidity. Okay, so here's one of my favorite examples. And so you take a molecule that looks like this, you connect this, you connect that end to that end, and that end to that end, and you get two products, two things, and then you do another connection, and you get this cylinder-y looking thing, and you get these two Mobius ladders. This graph with 6 vertices, 1, 2, 3, 4, 5, 6 vertices and some number of edges, that's called a Mobius ladder. Okay, it was in the math literature. Okay? So you embed a Mobius ladder in three-dimensional space, and suddenly you end up with two enantiomers, a right-handed twist and a left-handed twist. Okay? And these things are chiral, even given infinite flexibility, total unrestricted movement, just like Kekulé was saying, and yet they're stereoisomers. Okay? So that's really, you've broken down this strict separation between connectivity and Euclidean and geometry, chirality, right? Which is kind of cool. And then you have these things, and how do you prove which one is this one and which one is this one? Okay, so what's the most famous property of a Mobius strip? Have you ever heard of a Mobius strip?
Yes. It goes around.
Okay, so it does go around and around. So what's the most, like in elementary school, your teacher made a Mobius strip out of a piece of paper. What do they do with it?
It becomes only one ring.
Yeah, you cut it in half and it stays in one piece. That's the most famous property of a Mobius strip. So these things are carbon-carbon double bonds, and you can cut them with ozone. So if you cut this thing, you end up with two pieces. If you cut those 3 double bonds, you end up with 2 rings. Whereas with the Mobius ladder, if you cut these 3 bonds, then you end up with 1 big ring. Okay? And so you can actually do that, and that's how you prove the structure. Yeah, you get this big thing, and from this one you get these 2 littler half as many. So, yeah. All right, so then I was telling you that there are these molecules that are achiral but always chiral. Okay, so the Mobius ladder obviously is chiral. It's chiral. There's 2 enantiomers that are resolvable, it's chiral. Okay, but this molecule that was designed and synthesized by Kurt Mislow in order to prove a geometrical theorem, which Kurt is always saying, well, he's a sort of the patriarch, or the kind of the main dude in American stereochemistry. He's still alive. His career at Princeton, and so he says, it's possible to get these molecules that are always chiral and yet can't be resolved. And so he actually, he had the geometrical, it's a theorem, right? You can prove it. That's proof. But of course, Kurt had to make a molecule that proved his point. So if you synthesize this thing, now this ring and this ring, these benzene rings are flat, and the dihedral between those 2 planes is 90 degrees, and it's locked in because of these 4 nitro groups that can't get past each other. Okay? So the 2 rings are locked in at 90 degrees, the dihedral, and they can't rotate around that central bond. This is a single bond, but you can't rotate around that bond, because if you did, these 2 groups would be taking up the same space, and that doesn't happen. Okay? So this and this, these are mirror images. Okay? So you might say, well, this thing has these 2 enantiomers. Okay, but it turns out that you can take this, you rotate the central piece by 90 degrees, And you get that. So this can actually deform into this. But at no point in the deformation does it ever get achiral. This is also very counterintuitive. And I've had people tell me that that's impossible. Okay? How can you have something that's right-handed, deform it into something that's left-handed, without going through something achiral in the middle? But of course, that's easy, and you actually do it a lot, because if you take a rubber glove that has left-handed and right-handed gloves, you put a right-handed rubber glove on your right hand, and then you take it off and turn it inside out, it turns into a left-handed glove. But in that deformation, it never got achiral. Right? So this happens all the time. So, so that's why I call this a Euclidean rubber glove. It's like a rubber glove, right? It goes from right-handed to left-handed, but never gets achiral in between. Okay? So, and so Mislow synthesized this thing with these two menthol enantiomers. So, this is the mirror image of this. And so if these two rings could get coplanar, this thing would have a plane of symmetry. It would have a mirror plane. Right? If the two rings could get coplanar, there would be a mirror plane, but the two rings can never get coplanar. They're at 90 degrees. So you have to you have to rotate around both of these bonds at the same time. Rotate the central piece 90 degrees to get to the mirror image. So, yeah. Okay, so okay, so that doesn't require Euclidean rigidity. Notice, in this case, it's the Euclidean rigidity. It's the lack of unrestricted motion. It's the fact that you can't rotate around this bond, that makes this thing always be chiral, even though it can't be resolved. It's always chiral because you can't get these two rings into the same plane. Okay? But it turns out that, is that possible to do topologically? Can you have something that has infinite flexibility, no constraints at all on any motions, and still get from right-handed to left-handed without ever going through something achiral? And the answer to that didn't come until, like 1987. And Erica Flappen published this paper. If you look at one of these topology papers, I can get through the first couple words, and that's it. And every low-dimensional topologist in the world has to look at the paper and say it's okay before it can get published. That's why it takes them like years to get papers published. Anyway, Erica proved this, so I'm not just using physical models or making it up. But this is a figure-8 knot. It's one of the few amphichiral knots. It has a minimum of 4 crosses. Okay? The figure-8 can be deformed into its mirror image. It's amphichiral. You can go from one-handedness to the figure-8 and get to the other-handedness. And in fact, the figure-8 actually has a rigidly achiral presentation or shape, conformation, okay, where you have a let's see, that's a left-handed twist back here, and at 90 degrees a right-handed twist down here. So if I rotate that thing 90 degrees through this axis, and then I reflect perpendicular to the axis, I get back to where I started. It's achiral that has reflection symmetry. But if you just put a couple of colored points on the lines, these things can scooch around, like in math, in topology they have these very precise words. Like if I take this colored thing and scooch it, move it along the line, it's called scooching. Okay. But these two colored dots can't pass through each other. Okay, so it's just a colored graph, and this graph can deform into its mirror image, but having these colored points destroys the reflection symmetry. Okay, so this thing can never, even given infinite flexibility, it can never become achiral rigidly. It can never become achiral rigidly, and yet it can deform into its mirror image, so it's resolvable. It's not resolvable, sorry, it's achiral. Not resolvable because it can deform into its mirror image. Yeah, so we're done. Well, you can ask me later. I know this is looking pretty weird, but we're going to get to liquid crystals